All right. So based on request of precisely one person, we're going to make a very quick video on CNNs, like a really quick high-level overview. Let's try to make it 5 minutes. And so you're not going to be a professional in CNNs, but at least you'll have a pretty good understanding of computer vision and how it works. So myself, my name is Rami, bachelor's applied math, master's data science, working in ML ops and engineering space since the early 2020s, teaching math for about over a decade. So computer visions, what can you expect from this 15-minute, we'll say maybe 5-minute lecture? We'll spend a little bit on the background and some more time on the technical part, but 2 times as much. Computer vision tasks are broken up into 3 main categories. Classification, which basically you are just going to identify whether something exists in that photo or not. And if it does, what is it? Did you train, do you have a model trained on all the different types of animals? So within this picture, which animal is it? Is it a lion, a dog, whatever? Now the detection, second part, is we're kind of taking a step further. We're going to actually detect within that image where that animal exists. And the final one is segmentation, where we're actually able to extract within that image the actual the thing from the background. So we're going to distinguish it from the background. The annotating box is not going to be just a box now, but it's actually going to be cut out around the actual background. So there's a lot of practicality still in computer vision models in the modern day. With the war happening in Iran, US has came out and publicly announced that they're using OpenAI and Anthropic. They haven't said exactly for what, but it's pretty obvious, I would say, that they're using it to scan massive amounts of satellite imagery. Obviously, Iran is massive. And so what they're going to do is allow the computer to automatically detect if there are some, targets within that location. Medical diagnoses. Some researchers came out and said, computer vision is even more accurate in diagnosing than humans themselves. Obviously, self-driving cars, they have their backbone, the fundamental technology behind is computer vision. Computer vision works mostly on images, but the jump between a single image and a stream of images, which is what a video is not that big. Is this still relevant today? Why don't we just use ChatGPT? The foundation models, ChatGPT and Anthropic and Gemini are really good for general purposes. But if you're in a business, you may need more higher accuracy than what these things are going to offer you. So you need to develop a model or fine tune a model on your specific data set to get higher accuracy results. Depending on your use case, if you're using this model at scale and you're outsourcing it to ChatGPT, your costs are going to be enormous. So having your own model is going to save you thousands of dollars. You may need this model to be local on your computer, right? API requires an internet connection to whatever, to using ChatGPT and Anthropic. Latency. Maybe you need real-time analysis. Maybe you need sub-second analysis. Privacy and data security. Can we trust these, companies with our data? We may have clients or people we work with that don't even want their data anywhere near the internet. So we may need these models to live locally on our machines, on our servers. Interpretability. You may need to actually know, you see how I said that really fast? Interpretability. Because maybe, yeah, it's a hard word to say. If you have these models yourselves, you can actually look into them and see, you can do feature analysis. You can actually see why they're making the predictions that they do. Obviously, with ChatGPT, you can't do that. So if you're learning AI and ML, this is where CNNs are, right? You have a basic foundation in gradient descent algorithm, backpropagation, forward propagation, difference between inference training sets, testing sets. You have a fundamental understanding. And what you're going to do is just build on those. You'll see that CNNs have an extra part, the CNN stack, but the part that comes after, the fully connected layer, you already know that. So you're just building on what you already know. Really quick background into the history of CNNs is that They used to process images using fully connected neural nets, but that missed the geospatial components of it. With neural nets, you're allowing every input cell to have an equal weight as every other cell. Obviously, there's training, and other cells are going to have higher weights at the end, but the results were not great. Then in around 1980s, scientists who were working on vision, trying to understand how humans perceive, how they understand, came up with this idea of the local receptive fields. 1990s, Jan LeCun and his team implemented this programmatically. They came up with the very first kernel, the very first LeNet, this this model that works pretty good. They had some outstanding results. In 2012, University of Toronto's team with Ilya Sutskever, the lead research engineer at OpenAI, and then Jeffrey Hinton, their team basically made deep learning much more efficient. They leveraged GPUs, and they also introduced many other ideas. And so it sort of revitalized CNNs. All right, let's actually get into the technical parts here. So in a nutshell, you have an input image, goes in this black box, and on the output, you have a model predicting what likelihood this is given the class of potentials. So if you want to classify a letter, then you'll get from A to Z, you'll get a probability for every letter. And then if you have a good model, then it should tell you, every other value is low and C, for example, is high. So something a lot of people don't touch on is that, how long? How long have you been here? About 7 minutes? Okay. A lot of thing that people don't touch on is the difference between inference and training in these visualizations. If you're not too familiar with machine learning, then you should know this. In these visualizations, we're just doing a forward pass. We're showing you how an input goes in this trained model and you get an output on the other side. Different than training, where you have input, goes through the model, you get a value on the other side, it compares it to the actual label. So let's say it predicted a D and it was a C. It goes back, it does a back propagation technique, which updates the weights. And so you have this continual learning process. That's a training. For visualization technique, to basically give you a high level understanding, we're just going to do an inference. So we're just going to show you what we call a forward pass. So the CNN, if we break apart this black box further, this black box here, you see that it has two components. The convolutional component and then the fully connected component. That's it. You already know fully connected neural nets. If you don't, go learn about them. It's not that complicated. Within this convolutional component, there's three other components. The main part is the convolution. Then you apply a ReLU function, and then you do max pooling. Once we actually look into this, they're really stupidly easy. At first, it may take some time for you to wrap your heads around them, but even ReLU at first glance, it's really, really, I mean, all these concepts, they sound complicated. They're really not. Pictorially, here's how that architecture sort of looks like. Before we get into it, let's talk about the inputs. So the input is never an actual image. It's a matrix of pixel intensity values. That actually is what an image is. If it's RGB, so if you're not doing a black and white image, then you'll have three sets of these matrices. But if it's just black and white, you just have one. 0 is for black, 255 for white. You can normalize these further to make it between. Okay, we come here to the very first component, the kernel. Again, the kernel has been something that's been trained. These kernels begin randomly initialized. It goes through the training. In the training, then these kernels are trained. And universally, actually, in CNNs, you'll find that the very first layers in CNNs, the kernels are usually edge detectors. They're detecting if there's an edge. Here's how it works. You slide this kernel and you compute the dot product. The dot product is stupidly easy. You're taking 0 times 0 plus 0 times 0 plus 0 times 0, etc., and you get a single value. Now your output is that single value. Now I've converted it from a number to a pixel here, but you get the point. And you slide it to the next, and you get another value. All right. At the end now, we've got a feature map. Usually, let's say we have 4 kernels, so we'll get 4 feature maps. Each map corresponds to how much that input image was activated for that kernel across the entire picture. That was a lot of word salad. I didn't explain that good at all, but whatever. Sorry, I'm just giving you a high-level overview. And I myself don't actually understand it that very well. ReLU. Next, we take this output feature maps and we apply a non-activation, a non-linearity to it. So we're introducing a non-linearity, and ReLU is one of those activation functions. So you have 10H that we learned about. You have the sigmoid activation function. ReLU is just another activation function with the very simple rule that if it's less than 0, convert the number to 0, otherwise keep it. Visually, here's what it looks like. And in terms of CNNs, what you're really doing is you're attenuating the signal. So what you're saying, if the signal here is weak, let's make it really weak. Let's make it non-existent. And if the signal is strong, then we're going to maintain it. So in such a way, you're attenuating the signal and you're introducing non-linearity. Max pooling, the other fundamental concept in a convolutional stack. You take this pixel of value, you take a sliding window approach, and you look at the maximum value, and that's it. That's what you do. You slide it again, you take the maximum value. So that's it. You have done the convolution, the ReLU, and the max pooling. Depending on how deep your architecture is, you may do this set of processes multiple times. In our case, if we're just classifying letters, 2 would be enough. Even if you're recognizing digits, 2 would be enough. So let's do the whole thing again. But now we multiply by 2 the number of kernels. It's not a hard number. You can have any number of kernels in your second stack. Now it's a bit different. Now what we're doing is we're taking the dot product of each of the inputs. So before we just had 1, now we have 4. We add those together. So now at the end we have 8. And now we're actually beginning to go from edge detectors to the combination of edge detectors. And so the general idea theme is that the more you look at these feature maps as the number of CNN stacks increases, the more it actually begins to resemble something. There was a study that looked at the feature analysis of a model trained on recognizing human faces. And near the later ends, the input maps, the feature extractors, looked like one resembled a nose, one resembled eyes, one resembled a mouth and ears. Generally, the idea is that the more you increase in complexity, so the more complex your data set, the more necessary it is to make your network deeper and to increase the number of parameters in your network. The trade-off is you also need more data. Finally, once we get to the the very end, in our CNN stack or CNN process, we flatten the matrices for the purpose of doing a normal neural net. And we use a softmax to get an output on the other side. Now, a really quick thing about metrics, or yeah, what are the metrics used to determine how well your model is performing in object detection tasks? Before we get to those four main metrics, let's talk about these ideas of negative and false positives. If you've trained a model to detect chihuahuas and your test set has some cookies in them and chihuahuas, then if you've accurately captured a chihuahua, if your model had seen a chihuahua and determined it was a chihuahua, that's a true positive. If your model had seen a cookie and said it was a chihuahua, that's a false positive. If your model had seen a cookie and said it was a cookie or said it was not a chihuahua, that's a true negative. And if your model saw a chihuahua and said it was not a chihuahua, it's a false negative. Now, these are the four main metrics we can use, which we can see are combinations of the ratios that we learned previously. And the metric you want to optimize for depends on your data set, or depends on your task. Let me tell you why it's really important. If you're dealing with a heavily imbalanced data set, where let's say 99% is the positive class, let's say chihuahuas, and 1% are random objects like cookies and books and pens, then if you use accuracy and your model had just literally predicted everything as a dog, which it should do if you don't apply countermeasures, then your results, you're going to get 99% accuracy. If you're an evil person and you're deceptive, you can take that to your shareholders and you can say, hey guys, I've got a really good model here. Performs 99% accurate. If they don't know what you mean by accuracy and they don't dig deeper, right, then you're off the hook. Or if they actually want to see the model in production and live, and you feed it a doggy, you feed it a cookie, and it tells you that it's a doggy, then you'll also be exposed. So that's why these different metrics, you should use them depending on your data set.